Hello everyone. My proposed paper examine a phenomena that is familiar to some of you, the introduction of LLM-mediated vibe coding into enterprise citizen development programs, and asks a program-level question that is increasingly consequential for organizations. How does this new way of building affect delivery speed, solution quality, and governance performance when development is distributed beyond professional IT? The central premise is that citizen development is no longer only a low-code, no-code assembly activity. With generative capabilities embedded into platform, and technical builders can now produce executable logic and integrations through natural language interaction. That shift expands innovation capacity, but it also changes what control means because the outputs are probabilistic and the build process becomes less transparent by default. In this talk, I will establish the problem context, articulate the research tension and gap, and then introduce the research question and the theoretical framework that motivates the proposed hypothesis and study design. Citizen development programs emerged to address a persistent capacity gap. Business demand for automation and internal tools has grown faster than professional IT delivery capacity. Low-code, no-code platforms provide an organizational response by enabling domain experts to create applications and workflows closer to where operational knowledge resides. However, scaling citizen development has always involved a trade-off. As programs grow, organizations face fragmentation, inconsistent data practices, uneven quality, and the risk of uncontrolled solutions that bypass standard security and compliance processes. This is why mature programs typically develop governance mechanisms and enablement structures, training, templates, catalogs, and oversight pathways to balance autonomy with enterprise-grade reliability. So, even before generative AI, citizen development is best understood as a social technical system. Outcomes depends not only on tools, but also on program design, capability development, and governance arrangements. With that baseline, the key question is what changes when generative AI becomes embedded into the same platforms? Generative AI introduces a qualitatively different production logic. Instead of primarily configuring deterministic components, builders can now express intent in natural language and receive generated logic, code, or integration steps that can be iteratively refined. This practice is often described as vibe coding, an interaction pattern where progress is driven by rapid conversational iteration toward a working artifact. This matters because it shifts the competence profile of the citizen developer. The key skill is no longer only assembling and configuring, it becomes interpreting, validating, and hardening probabilistic outputs. The same feature that accelerates delivery also increases the risk of superficial validation. Accepting a plausible solution that works in a narrow case but fails under edge conditions, violates policy constraints, or become difficult to maintain. In other words, vibe coding changes not just productivity, but also accountability and the services where governance must operate. That leads directly to the central tension. Speed is easier to obtain, safe and maintainable speed is also the harder problem. There are two strong research streams that are relevant, but they rarely connect empirically. One stream examines citizen development and low-code, no-code governance, how organizations design programs that balance flexibility with standardization, prevent shadow IT, and achieve lifecycle accountability. The second stream examines AI-assisted programming and LLM-based development, evidence of task-level acceleration, improvements in specific software engineering tasks, and emerging methods for guardrails. The gap is at the intersection. Program-level evidence for citizen developers adopting vibe coding inside governed enterprise environments. Specifically, organizations need answers in operational terms. Does time to first working prototype decrease, and by how much? What happens to post-deployment quality and rework? Do governance incidents increase, and under what condition can they contained without introducing bottleneck that undermine the benefits. This is not a minor measurement issue. It shapes whether enterprises can responsibly scale AI-augmented citizen development rather than treating it as an uncontrolled experimentation. The paper's central research question is, in an enterprise citizen development program, what is the impact of introducing vibe coding workflows on innovation velocity, post-deployment quality, and governance outcomes? And how do program design choices moderate these effects? Two aspects of the framing are important. First, the unit of interest is the program context, not merely the tool. The same generative capability can lead to very different outcomes depending on whether the program institutionalizes structured capability building, such as discipline validation routines, and whether governance is designed to operate as embedded controls rather than slow XAND gates. Second, the theoretical framework treats this shift as algorithmic augmentation. What does that mean? Generative AI expands agency by lowering the cost of producing executable artifacts, while simultaneously requiring new boundaries of control to keep distributed innovation governable. Next, I will translate this framing into a conceptual model and hypothesis that specify expected relationships and moderation effects, and then I will outline a research design capable of testing them, or what I think capable of testing them. I'll be waiting for your comments, especially Marcello. Introducing the core logic of the conceptual model. The left-hand side is vibe coding adoption intensity, operationalized as the degree to which citizen developers rely on LLM-mediated prompting to generate and refine executable artifacts. The first pathway is the production engine. Higher adoption intensity reduces the effort required to translate intent into working logic, thereby accelerating iteration cycles. This motivates hypothesis 1. Vibe coding adoption intensity is positively associated with development velocity, typically measured as a reduction in time to first working prototype. However, the model does not assume that speed automatically produces better solution. The second pathway addresses quality, and it's explicitly conditional. Vibe coding can improve quality if it is coupled with structured workflows that support validation, such as interactive refinement routines, test-oriented prompting, and systematic checking of outputs. Without that structure, speed can amplify shallow validation and acceptance without understanding, increasing the likelihood of defects and rework after deployment. This motivates hypothesis 2. The relationship between vibe coding adoption and solution quality is moderated by structured capability building, such as the quality improves when structured capability building is strong and deteriorates or stagnates when it is weak. Presenting the control system side of the model, vibe coding reduces the cost of producing artifact, which increases the volume and complexity of what citizen developers can build. In a governed enterprise environment, that plausibly increases governance risk. Governance risk here is defined operationally as program-relevant events, policy-blocked actions, and approved connector attempts, missing approvals, unregistered deployments, and other observable control failures. This motivates hypothesis 3. Higher vibe coding adoption intensity is associated with higher governance risk events. The model then introduces governance maturity as moderator. The argument is not that governance eliminates risk, rather it changes the conversation rate between adoption intensity and violation. When governance is mature, through embedded controls such as connector allow lists, component catalogs, enforced registration, and real-time policy checks, the marginal increase in governance event should be lower at the same level of adoption intensity. This motivates hypothesis 4. Governance maturity weakens the positive relationship between vibe coding adoption and governance risk. Finally, hypothesis 5 specifies a design nuance. Governance that relies on rigid, slow stage gates can neutralize the velocity benefit and may encourage circumventions. In contrast, embedded low friction controls can preserve velocity gains while reducing risk because they operate at the point of creation rather than after the fact. With the model and hypothesis in place, the next step is to demonstrate a research design that can credibly test both performance and risk in a program setting. Summarizes the research design, the key methodological choice is to combine internal validity with ecological validity. The first component is a controlled build task study. Citizen developers complete standardized build tasks under defined conditions, such as with and without vibe coding support, and with and without structured scaffolds. This isolates causal effects on time to completion and task correctness under comparable requirements. The second component is a longitudinal program analytical study. Here we use real programs data from the citizen development platform and governance system to examine outcomes for actual internal solutions over time. This captures the operational reality that controlled tasks cannot, heterogeneous solution complexity, differences in criticality, diverse user skills, and real governance constraints. This two-part design allows the analysis to connect what we learn in controlled tasks, where mechanisms are clearer, to the field environment where program-level success is ultimately determined. Vibe code adoption intensity is measured using platform telemetry rather than self-report. Prompt interactions, AI suggestion accepted, and AI-generated artifacts event, normalized by development time and solution footprint. Development velocity is operationalized as time to first working prototype. Elapsed time from solution initiation or approval in the program registry to the first functional version that meets a minimal acceptance criteria. Solution quality is captured through lifecycle outcomes over a defined post-deployment window, such as 90 days rework, effort, and defect density, using operational records like incident tickets, change requests, and defect logs. Governance outcomes are measured as observable events, policy blocked actions, non-compliant connector attempts, missing approvals, and registration violation. This is important because much of the existing guardrails literature evaluates detection rates or benchmark safety, but programs need outcome matrices tied to operational control failures. Finally, the moderators are also measurable. Structured capability building can be proxied through training completion, assessment scores, and evidence of structured workflow, while governance maturity can be represented through an index capturing embedded control, breadth, and enforcement strength. Once measurement is explicit, the next issue is how to interpret adoption patterns. Adoption is rarely binary, and that matters for both analysis and governance design. Highlighting a practical point with major analytical consequences, adoption is not simple on versus off. In most enterprise programs, we expect a distribution. Many low-intensity users and small group of high-intensity users who build more often and push the boundaries of what the platform can do. This matters for two reasons. First, it shapes identification and inference. Program averages can mask tail risk if governance events are concentrated among high-intensity builders or high-critically solutions. Second, it implies governance should be tied rather than uniform. Low-risk experimentation can be enabled broadly, while high-intensity or high-critically work requires stronger embedded controls, additional validation expectations, and more structured enablement. Summarizing the expected pattern implied by the conceptual model and by some of my conversations with my clients. First, the model predicts that higher vibe coding adoption intensity is associated with greater development velocity. Operationally, we expect to observe reduction in time to first working prototype as LLM-mediated generation reduces the cost of translating intent into executable logic and compresses iteration cycles. Second, the model predicts bifurcation in quality outcomes. The key point is that vibe coding does not have a single uniform effect on quality. Its effect depends on whether citizen developers have structured capability supports and disciplined validation routines under strong scaffolding, such as guided interaction patterns, explicit evaluation steps, and validation artifacts. We expect quality outcomes to improve or at least remain stable as adoption intensity increases. Under weak scaffolding, we expect a deterioration or a rise in rework and defects because rapid generation can amplify shallow validation and acceptance of plausible but fragile outputs. So the expected empirically empirical signature is not simply AI improves everything, but rather AI improves speed and quality depends on capability building. This is precisely what makes the program design, training, and workflow institutionalization as important. Translating the governance side of the model into expected findings. The baseline expectation is that governance events increase with adoption intensity because the volume and scope of building activity increases and because LLM-mediated workflows can produce integrations and actions that less experienced builders may not fully anticipate. However, the model argues that governance maturity moderates this effect. When governance is embedded into the platform through allow list, constraint connectors, mandatory registration enforcement, real-time policy checks, and instrumented visibility, we expect the marginal increase in governance event to be meaningfully lower at any given level of adoption intensity. A critical implication is the preservation of velocity. Governance that operates primarily through rigid stage gates tend to introduce bottlenecks and may push work into uncontrolled channels. By contrast, embedded low-friction controls can reduce risk while allowing citizen developers to move quickly, because the system constrains unsafe actions at the point of creation rather than slowing the entire process through approvals. So the expected pattern is speed gains remain, governance events rise unless embedded controls are strong, and the best governance design reduces risk without eliminating the speed benefit. Summarizing the managerial implications, first, organizations should treat vibe coding as a program-level intervention, not a feature toggle. It changes role expectations, the capability profile required for success, and where governance must operate. Second, capability building needs to be explicit and structured. Citizen developers do not need to become professional engineers, but they do need to learn validation behaviors, how to translate requirements into testable acceptance criteria, how to probe edge cases, how to recognize when the model is uncertain, and how to harden solutions for maintainability. Programs should therefore institutionalize scaffolds, prompt templates, checklists, interactive refinement routines, and expectations for validation artifacts. Third, governance should shift left and become embedded. Instead of relying mainly on late-stage reviews, programs should enforce registration, constraint connectors, provide approved component catalogs, and instrument telemetry so that the risk is observable and controllable in near real time. Finally, the operating model should be tiered. Low-risk experimentation should be easy, while high-critically solutions should trigger additional controls and support. The objective is to preserve distributed innovation while ensuring solutions remain governable, auditable, and maintainable over their life cycle. Highlighting the academic contribution, first, the paper contributes or will contribute a unifying lens algorithmic augmentation to explain why generative AI in low-code, no-code environments is not merely a productivity tool, but a socio-technical reconfiguration. It shifts agency, changes how work is coordinated, and reallocate governance into platform infrastructure. Second, it advances the program-level measurement approach that the current literature lacks. Most evidence on LLM-assisted development is task-level. Most of the development evidence is qualitative and governance-focused. This paper specifies measurable outcomes that map directly to will specify a measurable outcome that map directly to program management, time to prototype, post-deployment rework, and defect matrices and governance events as observable control failures rather than abstract risk. Third, it will specify moderators that explain heterogeneity, structured capability building, and governance maturity. These moderators convert a general claim AI increases speed into more precise research agenda about the conditions under which speed becomes sustainable, high quality, and compliant. To conclude, vibe coding is likely to expand the practical ceiling of citizen development by accelerating solution delivery and enabling non-technical builders to generate more complex artifacts, but it also introduces a new class of quality and governance risk because development becomes more probabilistic, less transparent, and faster than traditional governance mechanism can handle. The implication is not to block vibe coding, but to redesign citizen development program around embedded controls and structured capability building so that AI-mediated development remains fast, accountable, and maintainable. The immediate next steps are empirical. Implement the measurement model, establish baseline velocity, quality, and governance rates, and then evaluate how these change as vibe coding adoption scales under different governance enablement designs. Thank you, and sorry for the long video.